So, a very good evening, everyone. Once again I welcome you all for the next session, and the next session will be taken by Professor Govind Pandey sir. Before inviting him and giving him the platform for the session, I would like to give a brief introduction about Professor Govind Pandey sir, who is currently working as a professor in the Department of Civil Engineering, Madan Mohan Malaviya University of Technology, Gorakhpur. Sir has published around 116 research papers in various international and national journals and conferences, and has authored 3 books and one book chapter in Springer Nature. He is reviewer of many reputed international journals, including journals published by American Society for Civil Engineering, Springer, Elsevier, etc. Professor Pandey is supervising 10 PhD theses and one PhD is already completed. He has also completed 115 MTech dissertation. Professor Pandey has organized organizational involvement in 25 seminars, workshops, conferences, and has attended 62 seminars, workshops, conferences so far. Sir was also the first and the officiating director of Rajki Engineering College, Gonda. He is also the principal investigator of CPCV funded project on ambient air quality monitoring in Gorakhpur city, and is also working as a member state level scheme sanctioning committee of a state water and sanitation mission, government of UP, Lucknow. Professor Pandey has also served as member of Board of Studies, Research Degree Committee, and Advisory Committee of various institutions. He is also nominated as a member of Management Committee as Educationist at Saraswati Shisu Mandir Higher Secondary. He is also served as a member of the Steering Committee by Government of UP Lucknow for implementation of New Education Policy 2020. It's our honor and privilege to have you, sir, for this ATAL FDP, 6 days ATAL sponsored FDP on remote sensing and GIS. Without wasting time, I would like to hand over this platform to you. It's up to you, sir.
Thank you so much, Ankur, for a very elaborative introduction. Although what you spoke is all by virtue of the contribution made by my distinguished students like you, who have been continuously putting your efforts in research and development at Madan Mohan Malaviya University of Technology, Gorakhpur, over the past few decades. It's my privilege to be here with you all, along with the distinguished participants from the various institutions belonging to the far-flung areas of the country, who are sparing their time this evening. So I offer my all good wishes at the outset on account of the new year to everyone who is on the screen now. And I appreciate that all of you are participating in this ATAL FTP, where I am now sharing some thoughts with you on a previously selected topic. I hope that I may be able to add something to your vast knowledge that you already have. And during the course of the delivery of the lecture, or even afterwards, I shall welcome any queries or doubts or questions from you, or we can interact on the questions of mutual interest as well. So if you agree, I may start, presenting the main, thoughts which are included in the PowerPoint presentation related to the lecture that I have to deliver for you to this evening. So should I share the screen? And
Yes, sir.
go ahead.
Definitely. Yes, sir.
Okay, fine. So, friends, I shall be sharing my thoughts with you this evening on the water and wastewater management in India, uh, specifically with reference to addressing the challenges in the context of climate change. As the domain knowledge which encompasses the use of remote sensing and GIS towards reducing the impact of climate change uh, 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 in a special context of your FDP that we are attending now. So we shall focus our attention around the main theme. If you uh, look at the topic of the lecture, why I have selected this one to deliberate with you, has its footing uh, in a bit to put our shoulders uh, to the wheel uh, towards reducing the impact of the climate change uh, in the country in particular, and in the entire world in general. And whatever knowledge we have, based on that only we plan our future activities. As you are all known that it is all the carbon game, which is uh, ultimately bringing about the climate change, which is going to be a very big challenge for humanity to face in the present century, as well as in the forthcoming century as well. Uh, you know that uh, ever since the beginning of the century, or you can say right from uh, year 1901 till the present year, we have experienced, the scientific calculations have shown that a zero point 0.7 degree centigrade rise in average global temperature has been recorded. And that is really a very, very big challenge that we are facing. And now we are estimating that by the year 2050, that change may go to the tune of about 1.5 degrees centigrade. Some pessimistic estimates say that it may even go to 2 to 4 degrees centigrade. But even if it is on the lower side, that is up to 1.5 degrees centigrade. So as of now, it is 0.7, and if it is say 1.5 degrees centigrade by the year 2050, it is going to be more than double. So and the various types of disasters which are associated with the climate change are well known to you, be it uh, the melting of glaciers and the effect on the rainfall pattern, the effect on the recurrence of droughts, or maybe the rising sea levels, or many more issues relating to the agriculture and food security, which remain a very big problem even now. And then, if it is further challenged by the changing climate, it will be very difficult for us to cope with us in a sustainable manner with the situation in future. So, with this in view, because water is essential for life, and whenever we consume water, we generate wastewater. So the management of both water and wastewater is of paramount importance to us. And during the course of water and wastewater management, what we need to do so that we could, contribute towards coping up with the challenges in the context of climate change, that I have tried to keep in the lecture, which will be delivered by me in a short while. There are, we shall be deliberating on the uh, 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 water resource and its scarcity, then the national and global scenarios relating to water, then water use in different sectors, water quality objectives, then wastewater issues relating to pollution load problems of the country, major water quality issues that we are facing, water quality monitoring in Indian scenario, water quality results of Indian water bodies, river basin-wise polluted stresses in the country, river water pollution control strategy, and the present approach, including initiatives of government for water quality management, which include, of course, the approaches which need to be, added with the special reference to the climate change issues, and then suggestion relating to water conservation measures, uh, need for strengthening and river action plan, and conclusion. When we let me go to the slideshow mode. Uh, uh, if you look at the global scenario of water, it appears as if it is a world of salt with about 97.3 to 97.5% of the entire water, uh, which is about which is covering about two-thirds of the surface area of the globe, uh, to be in the form of the salt water, which is neither fit for drinking nor fit for the active use for human consumption in many ways. And out of that, if you look at the fresh water, is only about 2.5%, and out of that also again, uh, more than two-thirds, that is 68.9%, is contained in glaciers and permanent snow cover, and it is there in the ice caps and the icebergs in Antarctic region also, which is practically unavailable for human consumption purposes, and only one-third, out of which also again only 0.3% is there in lakes and river storage, and 30.8% is in the form of groundwater, which again includes the soil moisture, and permafrost water, which are practically also not available for human consumption. If we look at that in another pictorial form, so you see the bottom slide where the freshwater lakes, that is uh, uh, about 67.4% water is there, and in the other wetlands 8.5%, soil moisture 12.2%, which is practically again not available for consumption. Rivers have only 1.6%, atmospheric moisture has 9.5% of water, which is practically again not available for drinking purposes or human consumption. Water retained in the plants and animal body is 0.8%. So whatever we see out of the total fresh water, about say 67.4% is in the form of freshwater lakes, 1.6% is in rivers, and 8.5% is in the other wetlands. When we summarize the whole scenario, we find that On the left side, you see the hydrologic cycle, wherein the moisture goes up by heating of water in the ocean, and then it is in that water vapor then comes down on the surface of the earth in the form of a rainfall, and then through surface runoff, it again joins through the rivers and lakes and other water bodies. Finally, it reaches the ocean. So that hydrologic cycle goes on in parallel. But when you look at the quantitative aspects, uh, you look at the groundwater in aquifers, it is only 0.59% because ocean water is practically unusable. Glacial form of water, which is in the form of frozen water, that is 2.51%. That is also
Slide is fixed, sir, not
unusable,
current
and
location,
only
sir.
0.59% of groundwater. And if you add up the lakes water, 0.0008%, river water, 0.0008%. So not more than 0.6% is practically available, not more than 0.6% of the fresh water, which we can use, which we can use for human consumption or for drinking. So, lot of water is there. 2/3 of the global surface is covered by water, but only 0.6%, even less than 0.6%, we can say, is practically available for us for consumption. So that is a very, very, you know, problematic scenario. And now you can say that water is not an abundant resource, which even though looks to be abundant, but it is not an abundant resource, it is a scarce resource, and it has to be protected and conserved with all sincere efforts. On the contrary, when you look at the global water withdrawal scenario, you see this is the world map depicting the global water withdrawal scenario in 1995, and just before the beginning of this century, and then in the present year 2025. These are the projected figures. And when you look at the color tones, the dark blue is that place where there is water withdrawal less than 10%, which is the best situation. Yes.
Slide is fixed, sir.
And then the light blue, which is 10 to 20%, light yellow 20 to 40%, and deep
Sir, actually,
yellow is 7.
your slide is not moving, sir.
So if you look at that, that yellow tone was not covering a large area in 1995, where the water withdrawal is 20%, or I am sorry, there was a small technical snag, so it was interrupted for a short while. So when we look at the scenario, we find that in 1991, the yellow tone, and that to the deep yellow tone, was covering a small area. That means the water withdrawal more than 20%, or in the range more than 40%, was limited to some areas only. But in 2025, you look at that, many more new areas have been added with the yellow tones. And look at our own country's map, India's map. In 1995, it was the water withdrawal was in the range 20 to 40%. Now it has gone up to more than 40%. So that is a scenario which must be looked into with all seriousness and sincere thinking, because if we have a very finite resource. Water is a finite resource, so that we have to use very judiciously and in a very conservative manner. Whereas on the other side, the water withdrawal is increasing day by day from 10% to 20%, 20% to 40%. And now in India also we have gone to 40%. And in all other, adjoining countries, it is, touching the figures more than 40%, which is a point of concern to us. When we look at the global water use, withdrawal and consumption scenario, that too, when you compare the whole thing from the beginning of the last century, from the year 1900 to the present year of 2025, in three major sectors of consumption. One is the agriculture, the other one is the domestic sector, and the third one is the industrial sector. If you look at the whole scenario, everywhere what we find that there are three, depictions which are clearly shown. One is the withdrawal with the darker tone, or the darkest tone, you can say. Consumption is with a different tone, and wastage is again with a different tone in all the three, sectors of consumption. If you look at agriculture sector, at the beginning of last century, it was about a little more than, say, 475 billion cubic meters in the year 1900 withdrawal, and now in the year 2025, it is likely to reach 3,200 billion cubic meters. So, and that is one side of the story, that the withdrawal rates are tremendously going up. And at the other, on the other side, if you look at it, the difference between the withdrawal and consumption is wastage. Now that difference is widening like anything. You look at the wastage in 2025 in 1900, and then you look at the wastage in 2025. More than that, if you look at the domestic sector, the wastage is so much that we can imagine how much how much wastage we are doing in domestic sector. The withdrawal is so much, the consumption is very small, and more than 80 to 90% is being wasted in one form or the other. Same is the scenario with the industrial sector also. On the contrary, the water available in the reservoirs, although it has gone up, but it has not gone up to the same pace as the consumption has risen. So on one side, we are spending more. It is like a bank account that we are spending more and depositing less in the bank account. So someday our bank account will be zero. We will not have any money. So same thing, same situation we are going to face, which is a point of concern for us. If you look at the river basin map of India, depicting the rainfall and the basins of different rivers, only a small fraction is there available as 2.5%, as we have already said. India is the wettest country in the world, but rainfall is highly uneven with time and space. extremely low, about say 150 millimeters in Rajasthan, and then very high in northeast, maybe even more than 11 meters in northeast. On an average, there are only 40 rainy days in the monsoon season of 120 days. And out of 4,000 billion cubic meter rainfall received, only about 600 to 690 billion cubic meter is put to use so far. So you look at that, out of 4,000, more than say, you can say 3,300 to 3,400 billion cubic meter is still wasted, and then it goes to the oceans in the form of surface runoff, or it joins the atmosphere or the soil moisture. And water resources are overexploited because of this reason, resulting in major water quality issues. And when we have water quality issues, we have to treat water. When we treat otherwise, if the water quality is bad, whenever it is uh, going from one water body to other water body, and there is some waste added to it, so that waste goes on decomposing, and that decomposition, if it is aerobic decomposition, it is going to generate carbon dioxide. If it is anaerobic decomposition, it may generate methane, it may generate even nitrous oxide and many other such gases, or carbon dioxide also, which may in turn cause the climate change issues due to the global warming caused by them. Now, National Water Policy, which was declared in 2002, it stresses the need for multi-sectoral integrated water resources development and management. And that is why we are, considering this discussion on water and wastewater management in India for today's topic. And as we have seen, India receives an annual precipitation of about 4,000 cubic kilometer, or 4,000 billion cubic meter, BCM, whatever you call, you may like to call it cubic kilometer or BCM, both are same thing, including snowfall. And out of this, about 75% is received during monsoons. And whenever we receive 75% monsoon in the monsoon season, we say that it is a normal monsoon. 75% and above is a normal monsoon. But if it is less than that, we say it is less monsoon that is expected that year. This is the rainfall map of India, where you find the green tone with very low rainfall, yellow tone with the moderate rainfall, and the red tone with good rainfall, and the intensity of the red tone or the colors will give you how much rainfall in what range you are getting. And if you look at that, there is a very, very wide variation. If you look at the northern portion of Jammu and Kashmir, Rajasthan, and a part of the northeastern region, we receive very small, scanty rainfall. Then the Deccan Plateau, Rajasthan, Punjab, and then some portions of Gujarat, we do not receive a very high rainfall, even less than the medium one we receive there. And then a part of the northern part of Uttar Pradesh, Bihar, West Bengal, Madhya Pradesh, Andhra Pradesh, Odisha, and West Bengal, then the northeastern states, and Himachal Pradesh, and then the coastal areas on the western side, and then on the eastern side also, we receive good rainfall. So there is a very wide variation, and because of the climate change issues, that variation has become even more erratic and more problematic, and it is likely to compound in the future years to come. The long-term average rainfall, annual rainfall for the country is 1160 millimeter, which is the highest anywhere in the world for a country of comparable size. That means nature has not done any injustice to us. We are very comfortable. We are quite rich in terms of the average annual rainfall that we are receiving so far in India. The annual rainfall in India fluctuates widely, as I told you, that it is the highest recorded at Mausinram near Cherrapunji in Meghalaya to the tune of about 11,690 millimeters. That is what I told, more than 11 meters. And in the northeast and in this region, the rainfall as much as 1040 millimeters is recorded in a day. So you can think of how much rainfall we are receiving at Mausinram near Cherrapunji. And on the other side, we have the places like Jaisalmer in the western part of the country, where we are having only about 150 millimeters of rain throughout the year. And out of the 120 days of the monsoon, as I told you earlier, from June to September, there are spatial and temporal variations also, and we do not have more than 40 days which we categorize as rainy days. When we look at the status of surface and groundwater resources in the country occupies about 3.29 million square meter geographical area, which forms about 2.5% of the world's land area. But it supports over 16%, which is now, I can say very comfortably, it is now 17% of the world's population. And if you compare this with the resources of land and water that we are having, so we are having 2.5% of the world's land area. That means about 1/50th of the world's land area. And on the contrary, we are supporting 17% of the human population of the world and 20% of the world's total livestock population also. Similarly, about 4% of the world's water resources we are having, that is 1/25th of the world's water resources, and we are supporting 17% of the human population and 20% of the world's total livestock population. So there is a huge pressure on our land and water resources in the country because of the very high human and livestock populations that we are supporting. When we look at the surface and water surface water resources and groundwater resources separately, and we refer to the National Commission for Integrated Water Resources Development estimates, the basin-wise average annual flow in Indian river systems is estimated as 1953 cubic kilometers or BCM, and the utilizable annual surface water of the country is 690 cubic kilometer only. So again, you see, it is more than 2/3 of the average annual basin flow in the Indian river systems goes as surface runoff, and then it finally joins the ocean. It remains unutilized. And when you look at the groundwater resources, the annual potential natural groundwater recharge from rainfall in India is about 342.43 cubic kilometers or billion cubic meter, which is only about 8.56% of the total annual rainfall of the country. The annual potential groundwater recharge augmentation from canal irrigation system, which adds up to this, is about 89.46 cubic kilometers or BCM. So total replenishable groundwater resource of the country is assessed as about 431.89 cubic kilometer, or in terms of percentage, you can say not more than 10%. So again, you can see the total replenishable groundwater resource of the country is contributed by total annual rainfall, not more than 10% of that. Remaining 90% goes to Indian river system and the other water bodies of the country, from where again only about 1/3 is used and remaining goes as surface runoff to the oceans. Now this was the scenario of the availability of resource. Now we come to the other part, that is the use of the resource. Now when you look at the water use in India at the beginning of the century in the year 2000, in different sectors you can see out of the total 634 billion cubic meters or the kilometer cube water which was used, about 85% was used in irrigation, 6.6% in domestic sector, 1.26% in industrial sector, 0.3% in energy sector, and 6.5% in the other sectors. If we look at this figure in general, we find that irrigation sector is receiving the lion's share in the water use pattern of India, followed by the domestic sector and the industrial sector. So, what we need to do when we talk about when we plan the water use in India in the coming years, we have to focus our attention to a very high extent on these three sectors, that is irrigation sector, domestic sector, and industrial sector. And we have to, on one hand, reduce as far as possible the water withdrawal, and on the other hand, we have to reduce the wastage as such. This is the annual water requirement for different uses in kilometer cube or BCM. There are three, predictions which have been included. One is in the base year 1997-98, then the other one in the year 2010, third one for the present year 2025, and the fourth one is for the projected figure of the year 2050. Now, if we look at the irrigation sector, there are two types of estimate: low estimate or high estimate, or the optimistic estimate and the pessimistic estimate. If you look at the percentage, now irrigation sector 2010 it was consuming 78%, 2025 it will be, look at in the year 2000 it was 85%, 2010 78%, 2025 it is 72%, and in the 2050 it is going to be 68%. Domestic sector it was 6%, going to 7% and 9%. Industrial sector 5%, 8%, and 7%. So what we see from here is that the use of water for irrigation sector is coming down year by year. Maybe if you compare it to 2000, 2010, 2025, 2050. Why? The reason is that on one hand, the land, more and more of agricultural land is being diverted for urbanization and industrialization. So land availability or the agricultural land availability is shrinking. Secondly, the availability of the irrigation water as it has been, because water use is also being diverted to many other uses. So that availability is also challenged for the irrigation sector. So because of that, use pattern is coming down. Domestic water pattern is certainly that consumption pattern is certainly increasing because population is increasing, and population uh, increase cannot be brought to zero. It cannot be made negative. So therefore, it is bound to increase, and let it increase under the checks and balances that we provide under our own social fabric system. For industrial sector, you see, it is 5%, then it has increased to 8%. And again, for 2050, it is likely to go down to 7%. Why? Because again, there will be a problem of resource crunch or the availability of raw materials for the industrial sector, which will be haunting the industry. And then the availability of the water again is going to be a big issue by the year 2050. Why? We shall just look into that aspect in a short while in some other slide. At the bottom of it, above the total line, if you look at that, evaporation losses. Evaporation losses are the losses from our water bodies. Now you look at that in the terms of the quantitative estimate. In 1997-1998, it was 36 BCM. In 2010, it has gone up to 42 BCM. 2025, it has come to 50 BCM. And 2050, it is going to be around 76 BCM. Now you look at the figure of 36 BCM and look at the figure of 76 BCM. It is going to be more than doubled. Why? The reason behind this is the global warming. Global warming and the climate change, which is causing this very heavy evaporation loss, which is going to affect not only our livelihood, not only our water availability for different types of consumptions, but also it is going to affect the availability of water in the various water bodies, including the dams and reservoirs, where we are planning the power generation, hydroelectric power generation, the canal irrigation, and many other things. So this is an eye opener to us for future also. And if you look at the trend that we have seen there in the last slide, the trends in water use in different sectors. So again, you either look at the bar chart or you look at the pie chart. The trend is very obvious that agricultural sector, even though it will be consuming the lion's share in future as well, but its consumption is diminishing. The consumption of domestic sector and the industrial sector is going up, and the evaporation losses are going very high. Now, this is very important to learn. As per the international norms, if per capita water availability is less than 1700 cubic meter per year, then the country is categorized as water stressed. When we look at the per capita water availability, when we calculate it, the method that we adopt is that for that country, we have the total availability of water resource in cubic meters, and then we divide that by the country's population in that year. So we get the per capita water availability in terms of cubic meter per year. If it is 1700 cubic meter per year or more, but for any country in the world, it is categorized as water stressed nation. And if it is less than 1000 cubic meter per capita per year, then the country is classified as water scarce nation. If you look at the scenario in India, per capita surface water availability in the year 1991 was 2309 cubic meter per year, which was much more than 1700 cubic meter per year. And in 2001, even though it came down to 1902 cubic meter per year, but even then also it was more than the desired target of 1700 cubic meter per person per year, and we were quite in a safe zone. But the problem is that these figures are projected to reduce to 1401 cubic meter per person per year in the year 2025 that we are living now, and in the year 2050 it is again to uh, uh, come down. It is likely to come down to 1191 cubic meter per person per year. That means that when we have embarked in the year 2025, we are a water stressed nation. We were a water rich nation till the year 2001. And from then onward, we have started diminishing. The reason is that water resources are limited, population is increasing, and that means that the denominator is increasing and numerator is limited, and that numerator also we are wasting. So we are reducing this. So this is really an alarm to all fellow countrymen that we have now to be very careful and watchful towards the water conservation issues, so that we may not, maybe the 1191 is not very high if you compare it with 1000 cubic meter figure, which will be taking us to be a water scarce nation. Maybe if not in the year 2050, maybe you can say that by the year 2060, we will be a water scarce nation also, which will be a very, very undesirable situation. So we must be preparing ourselves and planning in a manner so that we never reach that scenario of water scarce nation. But the biggest problem on the way that we see is the increase in the urban population. Because of that increase in the urban population, the water demand again, if you look at the bottom figure, low demand, medium demand, and high demand are depicted. So the water demand is exponentially higher, rising, and if you look at the state-wise net water requirement in the year 2010, 2050, and 2025 and 2050, for all the states it is depicted. For the entire country, the low estimate was 496 and the high estimate was 508 in the year 2010, which has now come to 584 in 2025 and 627 in 2025, the high estimate. And in the year 2050, it is going to be 759 and 9919. So it is going to be more than doubled. So population is also rising, the net water requirement is also rising, and the water resource availability is diminishing. Evaporation losses are increasing. So scenario is going to be very complex in the coming years. And at the same time, we are adding many pollutants. We are polluting the water resources. So the same water body which was containing good water for drinking or good water for irrigation or good water for human consumption for in many other ways is converted to wastewater, is converted because of the use in the domestic sector, it is converted to domestic sewage. Its use in the industrial sector, it is converted to industrial effluents. And by use of many, fertilizers and artificial fertilizers, of course, and many insecticides and pesticides in agricultural system, we are getting non-point sources of pollution through the agricultural runoff also, which are polluting our water bodies, and then creating a very serious water quality issue of various rivers in the country. Look at the pollution issues of our the pious rivers like River Ganga or River Yamuna, River Gomti, River Godavari, River Kaveri, River Krishna, many other rivers. They're all being victimized by pollution in one reach or the other. So that needs to be properly looked into and properly handled. Now, disposal of the domestic sewage from cities and towns is the biggest source of pollution of water bodies in India. When you look at the class 1 cities, I would say 423 class 1 cities and 499 class 2 cities. About 80%, in fact, there remains a gap of sewage generation and installed sewage treatment capacity. And this percentage gap is about 80%. That means we are not able to treat about 80%, maybe more specific, you can call it to 78.7%, or maybe if you come to the year 2025, you can say we are still not able to treat more than 70% of the sewage that we are generating in all our class 1 and class 2 cities. Similarly, when we look at the industrial sector, again, although we say that we are able to treat about 60% of the industrial wastewater, but the remaining 40%, which is untreated, is a very high strength wastewater and puts up a very high pollution load in our river systems or the water bodies of the country. And then at the same time, sometimes we have also been, coming across the episodes of bypassing of the industrial effluents by the industrial units, which again creates the problems for our water bodies in turn. And non-point sources of pollution contributed by the use of artificial fertilizers and pesticides, particularly the countries where the agriculture is the main business in the rural areas, like the Andhra Pradesh, Haryana, Punjab, Tamil Nadu, West Bengal, Gujarat, Uttar Pradesh, and Maharashtra. Lot of, say, more than 1 lakh ton per year of the pesticide consumption is there. Very small part of the pesticides or insecticides are needed in the agriculture, and the large portion flows with water either as surface runoff and joins the water bodies and pollutes them, or may it percolates the soil strata and then it pollutes the groundwater also. And certainly the domestic sewage or the industrial effluents, which are not properly handled, which are not properly treated in the in the urban areas, they sometimes get stagnated within the city. They are breeding places for the mosquitoes, and they again further contaminate the groundwater, and they contaminate the source of drinking water also in many cities. And the diffuse pollution, which is from the agricultural runoff, from the agricultural fields and the industrial effluents, they are the sources of the nutrients like nitrogen and phosphorus in many surface water bodies, particularly the lakes and reservoirs, which cause eutrophication. We have seen the case of eutrophication of the famous Dal Lake in India, and similarly many of our big lakes, they are also suffering from the problem of eutrophication. And when this nitrogen goes, it is oxidized. It may be converted to nitrous oxide, which has a global warming potential, or the carbonaceous organic matter which is there in the water bodies, which is either oxidized through aerobic bacteria to generate carbon dioxide, or through anaerobic bacteria to generate methane and carbon dioxide. So all these gases ultimately contribute to the global warming potential, and they become a source of climate change or the temperature rise. And with that context, we refer to the major water quality issues in our water bodies. The common issues are relating to the pathogenic or the bacteriological pollution, salinity of water, and the toxicity because of the micropollutants and other industrial pollutants. In surface water, primarily we need to deal with eutrophication of water bodies, depletion of oxygen. Many times you might have seen the fish kills in the lakes and reservoirs because of the oxygen depletion. And then referring to the ecological health of the water body. And in groundwater, we very often have to deal with the problem of fluoride in groundwater, nitrates in groundwater, arsenic in groundwater, iron in groundwater, and in coastal areas, the problem of seawater intrusion also. Based on the quality parameters, the use-based, which we call as designated based use-based classification of surface waters, is categorized from A, B, C, D, and E for 5 classes. The best class is A, and the worst class is E. None of our, pious rivers like Ganga and Yamuna, they are in class A in their entire length. Some of the stretches have been polluted heavily. Somewhere you find them in class B or class C, or sometimes in class D also. So that is the situation where we stand today. These are the drinking water quality standards, put up by Bureau of Indian Standards, the norms of ICMR and the Central Public Health and Environmental Engineering Organization, which may be of interest to some of you, that what type of water, what quality of water we require in India to drink, particularly by human population. When you look at the wastewater generation and treatment, you look at in class 1 cities and class 2 cities. In class 1 cities, the total generation is around 64.26%, and then in class 2 cities, it is, you can see, 8.91%. And when you look at the treatment part, only about 26.49% is treated in class 1 cities, and only 0.34% is treated in class 2 cities. So there are two important things to notice from here, that even though a large portion of wastewater is generated from class 1 cities, but a very large fraction of sewage or wastewater being generated from class 2 cities goes untreated. Only 0.34% remains treated. When you look at the scenario of industrial pollution load in India, out of maybe 150,000 manufacturing industries in the country, about 60,000 are polluting in nature, and the total wastewater generation is to the tune of about 14 to 15,000 MLD, out of which about say 8,500 to 9,000 is treated. The comparison of the industrial and domestic pollution load is shown here. You look at that in terms of the wastewater generation, that is the quantitative in, aspect in million liters per day. Then biochemical oxygen demand before treatments, biochemical oxygen demand after treatment in tons per day. Now you look at the wastewater, that is industrial and domestic. Industrial is on the left side, and the domestic is on the right side in the brown color. Now, when you look at after the treatment scenario, before the treatment, you look at that, lot of industrial waste is generated apart, and then a good portion is being treated. But in the domestic waste, lot of domestic waste water is generated. Lot of BOD load is also there, but only a very small portion is treated. That is, that you can see in the bar chart on the right hand side. Then outcome of the industrial pollution control in terms of reduction of pollution loads. So you look at the BOD load and COD load. So what is BOD load before treatment and what is BOD load after treatment? Similarly, what is COD load before treatment and what is COD load after treatment? So it appears that a good pollution load is handled in the treatment, but still lot of pollution load remains to be treated in the years to come, for which the treatment capacity has to be developed by the country. This is the statewide generation of BOD load after treatment, which you can say that it is a kind of organic load estimation. And we are delivering this lecture in Uttar Pradesh. And if you look at the figures of Uttar Pradesh is contributing 19%, which is the highest in the country. So we are one among the biggest polluters. We may be cursing a particular state, but if you look at the scenario, you look at Bihar, they are contributing only 2%. You look at Punjab, they are contributing only 5%, Haryana only 3%, Orissa only 1%. So sometimes we say that a lot of industrial development is there in Gujarat or Maharashtra, but you see, they are even contributing BOD load less than what we are doing. So I don't say that we should curb all our activities. I mean to say that we must be very sincere and honest, and we should put our dedicated efforts to treat the wastewater load that is generated in our states, respective states. Then it is a scenario in terms of the class 1 or class 2 cities. So in class 1 cities, the number has grown. It is with respect to 1978, 1988, 1995 and 2003. And number, as it has grown in the left side, then the population that has grown on the right hand of that, then water supply that is needed on the again right hand, and wastewater that is generated, and the treatment of wastewater which is being. If you look at that, the water supply has risen like anything. The wastewater treatment has also risen like anything. All in all the periods, but the treatment has not gone up in a proportionately comfortable manner. Same thing is true for class 2 cities also, but the differentiation that you see here is that the water supply and wastewater generation have increased like anything in class 2 cities also, but the treatment is very, very minimal. So we have to focus our great attention on class 2 cities where the treatment facilities are either non-existent or they are existing in a very, very weak chain. So we need to strengthen our treatment efforts in the class 2 towns of India or small towns of India. Then this pie chart shows to you the pollution load due to 17 categories of highly polluting industries. You look at that, the maximum load is put by distilleries, then followed by textile industry, then the engineering industry, then the pulp and paper, and the remaining other 22% by the other industries. We have put up the Ganga Action Plan way back in 1980s, where when we had found that the sewage collection system was either partial or non-existent, and the interception and diversion of drains for capturing the wastewater for the purpose of treatment which was desired. Then the treatment plants were put up at certain major cities. Their operation and maintenance of the sewage treatment plants was to be put on priority, wherein those days, now the situation has a little bit improved. The availability of power supply was a major issue, and the availability of skilled manpower was also a point of concern. This is CPCB report based depiction on the performance evaluation of sewage treatment plants in metropolitan cities, class 1 cities, class 2 cities, and the total scenario. There is a pie chart which will elaborate this scenario better. In metropolitan cities, you can see that out of the entire sewage that is generated, about 51% is treated. In class 1 cities, out of the entire sewage 35 558 MLD which is generated, 32% is treated, and in class 2 cities, out of 2696 MLD that is generated, only 8% is treated. So we have to focus our attention more on, I don't say that we don't have to, be careful about our metropolitan cities, but we have to focus our attention more on class 2 and class 1 cities in the years to come. Then I shall be very fast because the time is also running out. So in order to make sure that the water quality is good, so in the water quality, in the water bodies of the country, certain water quality monitoring objectives have been identified for national planning of pollution control, strategy and their prioritization, to assess water, nature and extent of pollution control needed in different water bodies or their part, to evaluate effectiveness of pollution control measures already in existence, to evaluate water quality trend over a period of time, and to assess assimilative capacity of a water body, thereby reducing cost of pollution control, to understand the environmental fate of different pollutants, and to assess the fitness of water for different uses. And when we go for that water quality assessment, we do it primarily either in the form of monitoring, where a long-term standardized measurements in order to define the status or trends is needed, and or surveillance, where the continuous statistic measurements for the purpose of water quality management and operational activities is done, and surveys, where a finite duration intensive program to measure for a specific purpose is adopted. Setting out the objectives for water quality for monitoring, whether it is to be a baseline or trend or flux monitoring, or the surveillance where it is to be done for water use or for pollution control, or for survey in terms of the classification of the water body or for management and research. These objectives which are shown here are selected, and then based on this we have a national water quality network, water quality monitoring network, which covers about 450 rivers, about say more than 154 lakes, tanks, ponds, creeks and seawater, canals, drains, etc. And then certain water treatment plants and then groundwater stations also. And for that, Central Pollution Control Board has a National Water Quality Monitoring Network where they have established stations. Now they have good number of stations where the monitoring of the water bodies can be done. The criteria for selection of monitoring station is there. We will, just consider that there are many, issues which may be looked into when we have a very fixed criteria, like water intake point for community water supply, if it is to be done for a city or town, or presence of large or medium or cluster of small water polluting industries is there, or places of religious basing, like we have to be watchful about water quality for the such places like Varanasi or Prayagraj, or many other places where religious bathing is done. Sources of river to get indication of its pristine quality, and these are the list of the parameters which are considered. These are the various parameters which include some about 9 core parameters, 7 field observations, 19 general parameters, then 3 biomonitoring parameters, 9 trace metals and 7 pesticides. Major quality concerns that we have been facing are the organic matter and bacterial pollution of fecal origin continue to dominate the water pollution problem in India. Number one. And number two, pathogenic pollution as reflected through indicators, that is total coliforms and fecal coliform organic matter, as reflected through BOD and salinity, as reflected through conductivity and other inorganic parameters and nutrients, as reflected through nitrogen and phosphates, are the major water quality concerns. So that is pathogenic pollution, number one, pollution of organic matter, number two, salinity, number three, and nutrients, number four. When you look at the trend in water quality, the organic and bacterial contamination are continued to be critical in water bodies, mainly due to the discharge of domestic wastewater, mostly in untreated form. Secondly, the receiving water bodies also do not have adequate water for dilution. That is also very, very important to learn. And that is the origin or the genesis where you say that in Namami Gange, we have two principal objectives. One was Aviral Dhara, the other one was the Nirmal Dhara. So the second one relates to the Aviral Dhara, where the receiving water bodies also do not have adequate water for dilution. We need to augment the water flow into such streams. And therefore, the oxygen demand and bacterial pollution is increasing day by day. This is the water quality trend. If you look at that, when you look at that term in a pictorial view, you find that even though we have been making a lot of efforts, but the scenario has not changed much. That is the major point of concern. This is the water quality trend of BOD. This is for the total coliform in terms of most probable number in per 100 ml. This is in terms of fecal coliforms. So the scenario has not improved much. And state-wise riverine length under different levels of pollution. Now, there are three levels of pollution which have been identified. One, where the BOD is less than 6 milligram, BOD is more than 6, where the BOD is 3 to 6 milligrams per liter, and where the BOD is less than 3 milligrams per liter. So less than 3 milligram per liter is considered to be a stretch where it could be considered good, and then 3 to 6 is moderately polluted, and more than 6 is severely polluted. So in Jammu and Kashmir, you see out of the entire riverine length of 2291 kilometer, the entire length is in the range where it is neither moderately nor badly polluted. It is in a good shape. Same thing is condition with the Himachal Pradesh, barring 19 kilometers which are badly polluted. But look at Uttar Pradesh where we are sitting now. Out of total 5619 kilometer length of rivers, only 2473 is having BOD less than 3. 196 is in moderately polluted, and 1180 is severely polluted. And if you look at similarly, you can have a glance at the other states also. Look at the river water quality scenario in Assam, Meghalaya, Manipur, Arunachal Pradesh, Sikkim, Nagaland, Mizoram, and Mizoram. We must appreciate that in all these rivers, the river water quality is still very good. And we don't have any stretches which are either moderately polluted or severely polluted. And out of the total riverine length of about 45,043 kilometers in the country, only 30,266 is in good shape. Remaining maybe 15,000 kilometer length is either moderately polluted or it is severely polluted. This is in terms of the names of the rivers, how they are polluted, how their length is polluted. Look at the Brahmaputra river. None of the stretches in Brahmaputra river is either moderately polluted or it is severely polluted. But look at the rivers like Subarnarekha. Out of 289, only 79 is left in a good shape. Remaining is either moderately polluted or it is severely polluted. Look at river Ganga here at the top. Out of 12,690 kilometer length, only 7318 is in good shape. 3612 kilometer is moderately polluted, and 1760 is severely polluted. So such is the condition there. So water quality status evaluation, if you see, initially we had only 14% of our riverine length, which was either moderately polluted or severely polluted. Later on, it rose to say 19%, and now 19% is moderately polluted, and only 67% is relatively clean. So 1/3 riverine length is either moderately polluted or severely polluted. This is shown here through a pie chart also. Total riverine length under different water quality status. Again, you can see the yellow color is a good shape of water quality, and then this blue color is the moderate shape, and then the brown color is the severe shape. So if you look at the the state like UP or MP or Odisha or say Andhra Pradesh, Maharashtra, you look at the Maharashtra, only a very small yellow portion is left. You look at Bihar, no, yellow portion is there. So that gives you a relative standing of different states. Then this is river-wise depiction of the same thing. Look at Ganga, look at Indus, look at Brahmaputra. How much portion of these rivers is polluted? And if you look at that, the rivers like Ghaggar, rivers like Subarnarekha, they are severely polluted. The state-wise perennial riverine length where we are benefited in India is given here. The most benefited states could be Uttar Pradesh or Madhya Pradesh, Bihar, West Bengal, Odisha, Andhra Pradesh, Maharashtra, then this Karnataka, Tamil Nadu, and Assam. They are the biggest beneficiaries. And this was the scenario which I was trying to discuss. In 88-89, only 10 polluted states were there. In 1992-93, 37 states were there. In 2003, the number rose to 86. In 2007, it rose to 178. In 2014, it rose to 275. And in the year 2025, it is more than 325. So that number of polluted states has increased like anything. Like when you say जो दवा की तो मर्ज बढ़ता गया, it is like that only. The state-wise pollution states are listed here. You can have a glance at these because total number of states are all on different rivers. It is listed here. The list of polluted water states at different places where these polluted states have been identified. They have also been listed here. For all the states in the country, including Delhi, Gujarat, Haryana, Himachal Pradesh, Karnataka, Madhya Pradesh, Maharashtra, Meghalaya, Odisha, Rajasthan, Punjab, Tamil Nadu, Sikkim, Uttar Pradesh, West Bengal. This is water quality trend of river Ganga. If you look at that, from 2002 to 2011, these figures have been depicted. Look at the minimum figure, the mean figure, which is the red color, dark red, and the maximum figure. Not much difference you may find. So that simply means that somewhere when we look at the performance of our pollution control activities, sewage treatment activities, industrial wastewater treatment activities, so they, even though our efforts have increased, but they have not fetched as much of the outcome as it was expected. For example, when we look at the mean figure, in say the year 2025 to 2002, the mean figure was 2.5, and in the year 2011 it was 3.3. So on the contrary, it has increased. This is across the river Yamuna. In 2002 it was 7, mean figure was 7. In 2011 also it was 7. So not much change has taken place, and for that reason the government of India has come up with the Namami Gange project, where the union budget prescribed a sum of rupees 2,037 crores in the year 2014-15, along with a sum of rupees 100 crores for the development of ghats and beautification of river fronts at Kedarnath, Haridwar, Kanpur, Varanasi, Allahabad, Patna, and Delhi. And then two, major aspects were planned. One was the Nirmal Dhara, where it was planned to clean the rivers, and then the Aviral Dhara, where enforcing river regulatory rules, regional agricultural practices were to enhance and restoration and conservation of wetlands was to be done, and knowledge of management on Ganga through Ganga Knowledge Center was to be introduced. And then there was a scheme for rehabilitation and upgradation of existing STPs along Ganga, ensuring 100% sewage infrastructure, in situ sewage treatment plant in open drains. Then riverfront management, action plan for Char Dham Yatra in Uttarakhand, capacity building for urban local bodies, and the afforestation and the conservation of flora and fauna. So all these steps had been planned, and based on that, the assessment of the groundwater quality in metro city, so there was a focus on groundwater contaminants also, including salinity, fluoride, nitrates, iron, coliforms, arsenic, selenium, micropollutants, etc., including pesticides and toxic metals, and which were monitored. And for that, there was a need for the strengthening of the sincere efforts, operation and maintenance, effective efforts for industrial pollution control, use of alternative simple technology, reuse and recycling of wastewater, waste minimization, wastewater discharge standards, and then effective public complaint reduction and pollution from diffuse sources. These were identified to be strengthened for the future years. Approaches to water quality management through legal and institutional provisions and through technical provisions are listed here. Constraints in implementation of the water quality management plans in urban areas are also listed here, with which the main constraint is the water scarcity. The second constraint is an inadequate resources with local authorities. Polluter pays principle is not properly followed. High organic and dissolved solid bearing industrial wastes are there, which need to be handled. Large number of small scale industries are there, for which the common effluent treatment plant need to be established. Operation and maintenance of treatment facilities created, and the characteristics of the effluents are to be properly looked into and handled. And then the water quantity aspects are there, where a need for coordinated action, river basin wise planning, and the tackling a special problem of arsenic and fluoride are to be looked into. There are various water conservation measures which you all know. I don't want to list one by one. Most of you know what are the various water conservation measures which need to be adopted in order to conserve water, to save water, to avoid the wastage of water. Initiatives taken by Government of India on water quality management through various policies and acts are also listed here. You can look into these. And then there are several water pollution control strategies that have been adopted, so which are listed here. River action plans have been built. In fact, we are running very fast because we have run out of time. Then National River Action Plan is chalked out, and then the experiences from the Ganga Action Plan and from industries have also been chalked out, and the work based on that, Central Pollution Control Board has initiated some more works to handle the problem of water and wastewater treatment and management in various locations through the involvement of the local authorities, Gram Sabha and Panchayats, NGOs, and the people's group. I think this portion we can skip because this is for a specific region, Tarai region of Uttar Pradesh. So this is the, this slide I will just take half a minute for the eastern part of Uttar Pradesh. You look at the net groundwater last figure, last column, stage of groundwater development percent. So, Gorakhpur 70%, Madan 46%, Devariya 83%, 80%, Basti 71%, Sant Kabir Nagar They are exploiting more than 80% or 83% of their groundwater, which is a really a point of concern. This is a small scenario of a small region. Same is the situation for elsewhere also in the country. So we need to focus our attention on the groundwater withdrawal also, not only the quality issue, but quantitative withdrawal has also to be properly looked into and checked. Otherwise, if there is no water, you go to Delhi. Now you cannot withdraw any water. You cannot have a pump in the second statum because the water has been exhausted. So we will just skip these. This is for the local scenario. We'll just skip these one by one. And when we look at the conclusion, so to preserve our water and environment, we need to make systematic changes in the way we grow our food, manufacture the goods, and dispose of the waste. If pollution by agriculture is reduced, please think over it very seriously. If pollution by agriculture is reduced, it would improve water quality and it would also eliminate cost incurred for treatment of diseases. This is very, very important factor. Municipalities and industries need to carefully treat their waste discharges. Manufacturers should reduce water pollution by reusing material. Triple R principle, reduce, recycle, and reuse, should be followed, and chemicals and switching over to less toxic alternatives. Also, there is a need to encourage reductions or replacement of toxic chemicals, possibly through fiscal measures. Efforts should be made to restore landscapes and ecosystems, to protect water quality and aquatic and wildlife more efficiently. For maintaining the quality of fresh water, sustainable water quality management strategies are required to be evolved and implemented. Recycled and reuse of wastewater should be encouraged, and rainwater harvesting and artificial recharge of groundwater should be taken up on high priority. And then, wherever possible, the plantation of trees should be encouraged because they help us in many ways, but they will always help us in improving the groundwater recharge and then in also interrupting the surface water flows and checking the soil erosion. So with this, we come to the end of our lecture. It was a little more, we developed about say 12-13 minutes more than the slot that was prescribed to us. So I beg your pardon for that. But now it's open between you and us for any questions, any queries, or any suggestions, of course. You are welcome for that.
This session is now open for questions and answers. Anyone, please?
So we can come to the screen. We can skip this slideshow mode. And then,
Is there any question from any of the participants?
I think they might be waiting for the dinner also. This is a dinner time for many. Many might be getting late for the dinner also.
Yes.
No, sir. Actually, your presentation was too good. Sir, my question is that the data which you have represented in the PPT, to which year does that reflect, sir?
For which parameter are you asking?
Sir, industrial pollutions and all what you have said in the earlier graphs, representing Uttar Pradesh as 19%, Karnataka as 6%.
Those data relate to 2017-18.
Okay, sir. Okay, sir. Okay, sir.
In fact, I try to fetch the current year data also, but somehow they were not available. So the data which were available with me are those. But certainly some improvement would have taken. It is expected. But the scenario has changed also. But it has not changed much. What I wanted to emphasize that you might have seen the experience from the Ganga Action Plan, where we have seen the BOD trend and the COD trend of river Ganga and Yamuna. So not much of the change we have seen in terms of the mean values.
Yes, sir. Right. Thanks. Thank you.
Hello, good evening, sir.
Yes, please.
Sir, I have a question that how can community-based approaches and traditional water conservation techniques be integrated with modern wastewater management strategy?
Very good, question, having a very good suggestion also. In fact, we have been, when we look at our traditional practices, we have been very careful and concerned in water conservation measures, both in terms of our lifestyle management or agriculture management or the drinking water management. Many a time, I can just refer to it that whenever we have been using the surface water bodies since ancient times, you cannot find any example anywhere in any book or literature where even the demons would have been discharging their solid waste or liquid waste into the rivers, into the surface water bodies. They were always being worshipped. So if you are worshipping, so you will never, try to damage their pristine state. You will never try to do anything that is wrong. So in our traditional water quality management practices or water conservation practices, where to the tune of worshipping the water bodies, not allowing even a water to waste, we had been using, now we are doing, we are opening a faucet, opening a tap, putting, then doing some toothpaste in the morning, and in the meantime, we get a mobile call and go away, and that water goes on wasting. Those days, they had their own containers full of water, and then it was put in a bucket or some other, large container, from where they were taking another, lota or another glass of water for their consumption. So the wastage was minimized. The practices were so that the wastage were minimized. Now we have faucets. Now we have, modern, amenities in water supply, in wastewater management also. So what we should do, I don't say that we should return back to the stone era, but we should at least follow the good practices which were prevalent then. Like nowadays, we have got many such faucets where you are consuming about 40 to 50% less water. In some faucets, even 70% less water than what you are getting in the normal faucets. So if you are, you are trying to install faucets, water taps in your house, why don't you replace them? If you have, say, 20 faucets in your house, So replace, say, not all 20 at one point of time, replace, say, 5 in 1 month, another 5 in another month. So you can have in 4 or 5 months replaced all the 20 faucets, and then you are saving at least 60 to 70% of water which had been otherwise wasted. Similarly, whenever we are using water in bottles now for drinking, and sometimes you go to meet somebody, you have a small bottle, you drink a part of water in that, and at some place you throw away that water along with water. Certainly, you should throw away the water in the dustbin. That is a good practice. But before throwing it into the factory along the dustbin, along with water, better you find somewhere you put it on some plant. It will it will fulfill the need of that plant also. So what I mean to emphasize here is that you can always, and we should amalgamate our traditional good practices of water conservation with the modern practices of water supply and wastewater management. That is going to go a long way in water and wastewater management in the country towards meeting the challenges put up by the climate change. Any other queries or observations? I hope Dr. Das, your query is replied.
So, thank you, sir.
Yes, please.
I guess there are no queries right now, and even the participants are now leaving. Uh, in your session, there were around 170 participants. They joined, so it was a great and a wonderful session. I really enjoyed. Everybody has enjoyed, and I can see so much of the feedback in my chat box. So, on the behalf of Buddha Institute of Technology and as a co-coordinator, it is my privilege, and I take this privilege once again and from wholeheartedly. Thank you so much, and we're looking forward for more sessions in future also. Thank you, sir. Thank you so much.
I am grateful to all of you, all the fellow participants who have been very patient while I was presenting the lecture before them, and who have given due attention to the facts brought about by me before them in respect of the topic of the lecture. So I thank you all from the core of my heart, and particularly to the entire organizing team of the ATAL FDP led by Ankur Kumarji. You have really done a wonderful job in organizing the ATAL FDP on such a and such an important topic. And I also appreciate that you also gave me an opportunity to share my views and thoughts with the learned participants of the ATAL FDP. So thank you all, and thank you very much. And let's hope that we meet sometimes later again.
Thank you, sir.
May God bless you all.
And good night.
Thank you all. Thank you very much.
Thank you, sir.